First of all, I would like to thank organizers for giving me this opportunity to present you my talk. And the answer for the question is yes. It was mentioned that it's very dangerous to ask yes or no question. So this was a yes or no question, and answer is yes. And I think it's the second yes question, because you answered also yes in the morning. So I will present you my viewpoint on the information and its realization using physical devices. And it dates back to Landauer, who proposed it in the 70s. And what I did, I applied category theory to make it even more visible. Okay, so let's start. So first of all, I will present the resolution of Maxwell's demon paradox by Landauer. And then it will demand some additional clarifications which can be made by using category theory. But in order to do it, I have to say something about entropy and induced ordering, on the ordering which is induced by entropy. And then using this, I will present a categorical viewpoint of entropy. And I think this part will be the most nicer. It will be applications of this categorical viewpoint. Okay, so let's start. So let's start from Maxwell demon. Here is this demon in the flash. Consider the Gedanken experiment by Szilard in 30s. He considered a single particle in the box. It's ideal gas particle. And this particle is in a thermal bath with the environment which has temperature T. And we'll try to extract some work from this system, and we'll try to do it in a cycle. So we construct some kind of heat engine. Okay, so let's start. So in the beginning, we have a box, and we put some partition inside. To make it simple, I put it into middle. And we don't know where the particle is. Okay, so now we have to localize this particle. And for example, we localize it here. So this is task of Maxwell demon. So he localized this particle here. And he noted that the particle is here, so now we can start to extract the work. So we make this border to move to the right when this gas or particle hits this border, and we extract work. So this moves here, and we extract more and more work. And what's the quantity? So if we assume that this is equation of state for ideal gas, which is one particle, then we extract exactly this amount of work. It's exactly integral from half volume, because here's half volume, to the full volume. Okay, so and after that we take this border and put it again here, but we still don't know where the particle is after putting this border. So the cycle starts again. So our net gain is this work, this amount of work. But what thermodynamics says about this? So we know that we cannot extract the whole, only work from the environment. We have to, in some sense, we borrow some entropy from the environment, and then in order to preserve second law of thermodynamics, we have to return the same amount of entropy or even more. So the change in entropy should be positive or zero. And it results that this work which we extracted must be much larger or equal to the heat which we expelled to the environment. That's the second law of thermodynamics, but we don't have this expelling of the heat, so there is some problem with this. And the idea by Landauer in 70s, he was an engineer who works at IBM, was that he associated this expelling of the heat with erasing of memory of the demon. So demon noted where the particle is, and he used his memory to do it. So after after putting again this border inside, we don't need this information, so daemon delete it. And this deletion by Landauer was generating this amount of heat. So the heat expelled was equal or greater than this quantity. And Bennett used this idea to explain how to correct this experiment. So let's do it again. So in this 3 to 4 change, we extracted some work, and this work was this one. And now, after taking this border inside, so going here, we don't need information about localization of this gas particle. So we delete daemon's memory, and it expels this amount of heat. So if we do simple math, we see that Q is greater or equal than work we extracted. So everything is OK in this case. And that was ingenious idea. But for me, it was not so self-explaining, because I wanted to also associate some kind of memory, in the sense that considering this talk about robot's brain, I wanted to split sacrum from profanum. So ideal system of the memory, so bytes and Shannon entropy, from its realization, which based on thermodynamics and standard Boltzmann entropy. So that's the idea. So assuming that Landauer principle is right, because now this principle is under heavy examination, so it's not right to say it's true, but probably it's very true. So assuming this, we want to separate this information system from its realization on the level of physical system. So idea is that we take this information world with Shannon entropy and make from it a category in parentheses. And the second one is this thermodynamic system, which realizes this information system, and we also form from this category. And now we find some connection between this information world with physical world, and it will be something which appeared here, and it's called adjoint functors. Well, it's even simpler than adjoint. So the question is, what is this functors which connects these two words? And yes, there is some connection, and it's called Galois connection. It's a simplest example of adjoint functors. Generally, it relates to preordered sets, which are called posets for short. Okay, but how to find in this theory this Galois connection? So we have to define some ordering, because we need posets. Yes, because posets has ordering, and we need it to define Galois connection. So let's start from thermodynamics. And there is a geometric approach which use contact space with foliations which are induced by entropy. It was described by many authors. I summarized it in my paper. But it's not quite useful. One thing which is useful from this formulation is some corollary for second law of thermodynamics, which states that if state Y is reached by from X by adiabatic process, which is quasi-static or not, then entropy increases. That's the standard result. And here is this ordering. So I was glad to find some paper which used this idea to reformulate whole thermodynamics using axiomatic approach, and which is based on ordering. And it was done by these two gentlemen. So let's review very fast what it is about. So they assume that thermodynamic system is described by points x, y, z in some space gamma, and there are some additional conditions which results from thermodynamics. So, for example, if we have composite system, so system which consists of two parts or more, then the state is composite state from the Cartesian product of two spaces. And also, a system can be rescaled. Like, if we change volume by some scale, then the system should also scale. So there is action of some group on the system. It's right action on the system. So, for example, volume is scaled. Okay, and now the ordering. So we have the statement that y is adiabatically accessible from x, which is denoted by this symbol, which shows that it's some kind of order, when there is adiabatic process that transforms x to y. So there is some path or some change from x to y by adiabatic process. And of course, it fulfills this condition. So x is strictly less than y if x is less than y and not y is less than x, which is quite obvious. And x is equivalent to y if you can go from x to y and not from y to x, by adiabatic process, of course. Okay, and we have to be sure that this relation is a total order, because for sure it's only partial order. So it means that if we have two states, then they are somehow ordered one way or another. Okay, it's not true for chemical reactions because their entropy is much more involved. But if you exclude these chemical reactions, then you can assume that it holds. So we have total order, and it's called comparison hypothesis, which these two guys assumed. So this ordering has some properties. I maybe don't want to tell about them more. But the idea is that these assumptions are sufficient to make or to prove that entropy exists. And this is simply some kind of pullback of ordering from real line to this gamma system. And yeah, so the main result is that assuming this comparison hypothesis and this ordering, we have some function s from gamma to real numbers, which is called entropy, and it has this property so that if x is adiabatically accessible from y, then entropy behaves like this. And if we have composite system, then the entropy of this system is the sum of entropies, and this is behavior under the scaling. So we can take lambda from outside of the S. And if we have equivalence states, then entropy is the same for both. And also, if one state y is reached from x, but not the opposite side, then entropy is strictly preserving this relation. And it's also only for adiabatic process. So the headline is that this relation uniquely defines entropy up to multiplicative constant. Okay, so now let's do category theory. So we have our posets. So the plan is as follows. We have states in thermodynamical, for example, states, which forms G-posets. It's, G-sets. It's a set with scaling. And we add entropy, which introduce ordering. And we have assumption also on total ordering. So we have a poset structure. And this is what we need for Galois connection. And we have two such posets, like for information poset and for mix. We can make a Galois connection, which occurs that it is exactly, yes?
Sorry, what's G?
G is some group. In our case, is this R group which scales. Okay? Yeah, so it will be Landauer connection or Landauer principle. Okay, so first we have to define entropy system. So entropy system is this poset or G poset, which when we introduce also scaling inside. And objects are as states and some ordering. And there is a preserving group which preserves this structure of this poset, which is exactly definition of G poset. And this ordering is introduced by entropy function, some functions from the states to real numbers. And now how to reformulate Galois connections in terms of this entropy systems. So we have two entropy systems, G1 and G2. And Galois connection, which is denoted by this symbol also, like adjoint functors, it's exactly this condition. So it means that if, so there are two functors between G1 and G2 and from G2 to G1, and they preserves ordering by entropy. So if we move something in one system that change ordering, then if this second system is also Galois connected, then something change in the second system, according to this relation. That's the rough idea of this. Okay, and we have to also define something which is similar to adiabatic process, because we have this definition only for adiabatic processes. And for example, for information theory and Shannon entropy, we don't have adiabatic definition, so we have to put it inside our scheme. So adiabatic process is a sum map from gamma to gamma, so from space of states to space of states. And it's reversible when, for some point, starting point, we have P is equal to f of P. So it's invariant point of this mapping. And such that S of P is exactly, so it preserves entropy. Otherwise, F is called by me irreversible process. Okay, so this also works for entropic system, but for any system it also works. So this definition is general enough to use it for information system and for thermodynamic system. And here's my main theorem. So these tables are exactly Landauer's Landauer principles. So what does it mean? So we have one system with induced ordering by entropy, and the second one with disordering, and two functors as previously, from G1 to G2 and from G2 to G1. And in first case, when F is Galois connected with G, we have that this gamma 1 system processes, reversible processes, are realized by gamma 2 reversible processes, and reversible processes in gamma 1 are realized by gamma 2 irreversible processes. The only thing is that gamma 1 irreversible processes are not realized by gamma 2 reversible processes under this assumption. And the same is when we switch this Galois connection, so this table transposes. And if we have diagonal, say, table, so yes is here and here only, then we have that F and G are ordering isomorphism. So the mapping is, say, 1 to 1. And it's stricter than Landauer principle. Okay, so let's go to applications. So first application is Landauer original experiment. So we have here this realization which I show you with one particle of ideal gas. And we have realization, so order isomorphism of this state to some state of memory here. And this memory is realized by some physical system at level of, say, physics or thermodynamics here. I showed spins, but it can be electronics or something else. And so here we have reversible processes, but when we move from this state to this state again, we delete this information about the location of the particle from, so here we don't have this information. And here, at the level of physical realization of the memory, not at the level of memory, we have this heat which is expelled, so this Landauer heat. So that's the decoupling of two levels of complexity to well, I separated these two levels. And here is also another example or another drawing for this principle. So we have this original Demon-Maxwell device. We have order isomorphism with memory, which denotes how many particles are here or here. And there is realization on some physical memory chip, which is exactly Galois connections by these F and G functors. So that's the coupling. But there is also other system which can be also applied or can be described by these Galois connections. For example, I was interested in DNA computing, but it is also related for the meaning of life, roughly. So at the level of information, we have a genetic sequence, or we can translate it into bytes or bits. And at the level of its realization, we have biochemistry, which is a physical system which is governed by entropy. So everything which we do at the level of genetics or mixing genes can be or must be realized at the level of biochemistry. So if we do here some irreversible operation, then some heat will be expelled, according to Landauer theorem or Landauer connection. And then another example, which I steal from David Spivak's book, and which is also a good example for this application of Landauer principle, is evolution. So we have to construct two posets. The first poset is a population with ordering that population P is inside or less than Q if the animal species of P are also animal species of Q in the meaning of the tree of life. So on the tree of life, we have branches, and we have one species, and then from this evolves the second one. So the ordering is according to branches in this tree. The second poset describes gene pools. So G is a set of gene pools, and ordering is according to the inclusion of one gene pool into the second gene pool. And we have one functor from P to G, which sends population to gene pool that defines this population. And the opposite side, we have a functor which maps G to P, which sends gene pool to set of all animals which realize this gene pool. And of course, if you think a bit, it is Galois connection, because we have some ordering, and these functors preserve this ordering in both directions. So we can also think, but it's very abstract thinking, that if we make some irreversible operation at the level of gene pools, then there will be some heat of evolution. So if we evolve, then we introduce some heat, but this heat is very small because this constant, Boltzmann constant is very small. So it's probably not measurable, but still there is some idea. So conclusions is that it's very fruitful to categorify some nice examples in physics or whole physics, at least entropy for me. And Galois connections is very deep connections between models, so theories, which are ordered by the level of finiteness. So the more finite theory is after the broader one, and their implementations, which so some kind of realizations of these theories, and it's exactly Galois connection. So I found these Galois connections also in thermodynamics, which says that probably there is something more deeper, but I don't know what now. Okay, and as I said, this Landauer principle, or generalization of Landauer principle to Galois connection, describes a deep relation between models like memory or something which is abstract, and its implementation. So something which relies, for example, simulations, brain, and thermodynamics. Okay, so I would like to thank some guys who sponsored me. And here are papers. If you want to learn more, then probably this is a good starting point for this axiomatic approach. Here are my papers on this subject which I presented. There is very nice introduction to category theory. I learned a lot about Galois connections from this resource, and mentioned work of David Spivak from MIT about application of category theory. Okay, thank you.